In this video, we're going to be talking about accelerated motion conceptually, doing a couple calculations and a couple graphs. If you take a look right above the car over here, it shows that acceleration is the rate that velocity changes. One thing that's often misunderstood is acceleration doesn't tell you about how fast something is moving. It just tells you how quickly it speeds up, slows down, or changes direction. One of the first things we're going to do is we're going to use one of these green formulas to calculate the acceleration of this car. According to my diagram here, it shows that it starts at 3 meters per second and speeds up to a velocity of 15 meters per second in 4 seconds. So what I'm going to do is I'm going to label the variables that are given and then pick an appropriate formula to find the acceleration. Okay, so I finished solving for my acceleration. I labeled my known variables, my VI or V naught. My initial velocity is 3 meters per second. My final velocity is 15 meters per second, and my time is 4 seconds. So after analyzing these three formulas, I decided that the first one was going to be my best option because that was the only equation where I had all of the variables besides A, which is the variable that I was looking for right over here. So I plugged in all my variables where they belong, and then I didn't really have to do any algebra. Everything worked out pretty nicely, and my answer came out to 3 meters per second squared. What that means is as the car is traveling, you're adding 3 meters per second of velocity for every second that you're traveling. So looking at the number 3 with the unit meters per second squared after it is a little bit harder to understand conceptually. When it's written like this, it's a little bit easier to understand conceptually, but 3 meters per second squared is more of the standard way that it's written, but 3 meters per second is also acceptable as well. Okay, from here on out, what we're going to do is we're going to solve for the displacement, which is delta x. If I take a look at my other formulas, they both have a delta x in them, so they're both potentially able to solve for delta x as long as I have all of the variables. So let me go ahead and take a look at my list of variables. I have all of the three stated earlier, and now in addition, I also have that 3 meters per second squared for the acceleration. So if I'm taking a look at this formula right here, it looks like I need VI, T, and then acceleration, which I have all of those three. I have VI, I have T, and I have acceleration, so I'm able to use that second formula. The high majority of people would use that second formula because it's already set up to solve for delta x, so everything works out nicely where you don't have to do any algebra. But let me go ahead and take a look at my third equation over here. I do have VF, I have VI, and I do also have acceleration, so we can actually solve for it using the second or third equation. So what I'm going to do is I'm going to solve for delta x two different ways to see how they work out and see what I get for each of them. All right, so I completed solving for delta x using the second and third formula. Like I said, the second one worked out pretty nicely because I didn't have to do any algebra. I was just plugging in numbers into my calculator and I got 36 meters. So all that tells us is that the car moves forward 36 meters as it accelerates from 3 to 15 meters per second in that 4 seconds. For the second formula, it was a little bit more complicated with the exponents. I had to do a couple steps of algebra. I just went ahead and squared my numbers over here, and then I had to do 2 steps of algebra. I subtracted 9 from both sides. I ran out of room, so if I slide up over here, I see that I have 216 equals 6 times delta x, and then I divided both sides by 6, and then your answer becomes 36 meters, which is the exact same answer I got from the other formula. So there really isn't, a correct way to do it necessarily. Both of them work. As long as you have all of the variables you need for that particular formula, you can solve for delta x correctly. Okay, so now for the last step, I'm going to solve for, well, I'm not necessarily going to solve, but I'm just going to plot the graph for the position versus time graph and the velocity versus time graph with the information that I've solved for and with the information that's provided. Okay, I've completed our position versus time graph and our velocity versus time graph. I just sketched them pretty quickly, just plotting the main points and then showing the general shape of the position versus time graph and the velocity versus time graph. So for the position versus time graph, according to the information I have up here, I do not have a starting position, so I started at 0, but I do know that the delta x is 36 meters. So I do know it advanced forward 36 meters in 4 seconds, so I went from 0 to 36. As far as the shape of my curve, I curved it upwards so that it would show that the slope is increasing, because the slope is showing the rate at which it's moving, and the rate at which it's moving is increasing. Therefore, the slope is getting steeper as the time advances towards 4 seconds. Now for the velocity versus time graph, that one is a little bit more straightforward. I started at 3 meters per second, and I showed a steady increase up to 15 meters per second in that 4 seconds. For that one, the slope is constant because the rate at which I'm increasing my velocity is constant. I'm adding 3 meters per second of velocity every second. So I just have a nice straight curve for the velocity versus time graph. Okay, so that concludes a few different things. The concept of acceleration itself, how it's the rate that the velocity is changing, which is how it speeds up, slows down, or changes direction. We did a couple calculations so you can see how numbers are plugged in to solve for various things. And then also how a couple of the graphs look provided some of the information that we got. So thank you for watching and listening.